Okay, just a reminder that your midterm is on Wednesday. And you should download it off of Gradescope. You'll have 1 hour to complete the midterm, and it has to be done on physical paper. But because of that, I'll give you 10 minutes at the end to scan and upload your exam to Gradescope. So I guess class is supposed to start at 1:10, so you'll have until 2:20 to submit, unless anything that I just said was wrong, but I think that's right. And it'll cover up through lecture on Friday. So we were in the midst of talking about this idea of duality, right? Taking a vector space, you can take its dual, which is just the space of all linear maps from the vector space to the ground field. And given any map from V to W, you can take its dual to get a map from W dual to V dual. And we're right in the midst of trying to understand the properties of taking the dual of a map, right? So the last thing that we proved on Friday was that if you have a map, T, a linear map, then the null space of the dual is the same thing as the annihilator of the range, right? Remember, T went from V to W, which means that the dual went from W dual to V dual. So the null space should be some subspace of the domain. It's got to live here, right? Which means that we can't expect to take, I don't know, something about the null space of T, because the null space of T lives in V, which isn't that related to W. But if you take the range of T, that's a subspace of W. You take its annihilator, that's now a subspace of the dual of W, and it turns out that they're actually equal. Okay, so we proved that. We now have a nice corollary of that fact, which is the following. So now I'm going to suppose that V and W are finite dimensional. T is a linear map from V to W. Then T is surjective if and only if the dual map is injective. Okay, so a nice little pithy theorem. Why should I expect that this previous result should be helpful? Well, the injectivity of the dual map that's the same thing as saying that the null space of the dual map is trivial, right? So the injectivity of T dual should be related to this thing. On the other hand, the surjectivity of the original map T, that says that the range of T is everything. So the surjectivity of T and the injectivity of T dual should be related by this theorem. Okay, so let's prove this. Oops, let me switch colors. Okay, so we know that T is surjective. That the definition of that is that the range of T is all of W. Right, so it's surjective if and only if its range is everything. Okay, claim is that the range of T is equal to W if and only if the annihilator of the range is just the zero subspace. Okay, so if I could prove this claim, I would be done, right? Because the previous theorem says that the annihilator of the range is the null space of the dual map. And so that would show that the null space of the dual map is trivial, which would show that the dual map is injective. Okay, why is this true? So let's prove this in a different color, this claim. And so if range of T equals if range of T equals W, then certainly if you take the annihilator, it's the same thing as the annihilator of W. Right, well, what is the annihilator of W? This thing is supposed to be all of the linear functionals that vanish on all of W. But there's only one linear functional that vanishes in all of W. It's just the zero linear map, the zero linear functional. So this shows, whoops. This shows one direction. Right, so this direction is okay. Now, conversely, so I'll prove the converse by the contrapositive. Suppose the range of T is not equal to W. I'm going to show that the annihilator is not just the zero linear, the trivial subspace of the dual. So let's take a basis. Maybe let's call it V1 up through Vn of the range of T. And then we can extend this basis to a basis of W. Let's say V1 up through Vn, and then we extend it with some W1 up through Wm. Okay, and since the range of T isn't everything, it means there's at least one W, right? So since we're assuming that range of T is not equal to W, there exists at least a W1, right? We have a non-empty list. And the point is now we can construct a linear functional that vanishes on these guys, but doesn't vanish on any of those. Okay, so then we can construct a linear functional from, let's call it phi from W to F. Right? In other words, phi is in the dual. Well, you can construct any linear map by specifying what it does to a basis, right? So by phi of Vj equals 0 for all j, and let's say phi of Wj equals 1 for all j. Remember, we have this theorem that says that you can construct a linear map by specifying what it does to a basis, and you're allowed to send the basis anywhere. Okay, then phi is in the annihilator of the range, but phi is not in the annihilator of W. So this shows that, I mean, actually, I don't even need this. It's true, but we have, as we here, we have a non-zero map in the annihilator of the range. So this shows that this is not equal to just 0. Okay, and this is where we needed finite dimensionality, because you had to pick a basis of the range of T and extend it to a basis of W. If you have an infinite dimensional vector space, this claim is actually not true. It's possible to choose a subspace, a proper subspace that has 0 annihilator. You should think about this. This is an interesting problem. Okay, but now, since we proved this claim, once we prove this claim by the previous theorem, this is if and only if the dual of the null space is equal to 0. Sorry, the null space of the dual map is equal to 0, which is from a very old theorem, if and only if T is injective. Okay. So that's a nice result. And it's like sort of another one of these instances where this whole world of duals somehow is like you flipped everything upside down somehow, right? So like you have the map T, you have its dual, but then also like surjectivity and injectivity are sort of like opposite phenomena in some way. And so the surjectivity of T is like the injectivity of the dual map. Okay, so we've studied so far the null space of the dual map and the injectivity of the dual map. Okay, which means that you should think The next thing we're going to approach is we'll try to understand the range of the dual map and the surjectivity of the dual map. And you maybe even can guess what the range of the dual map might be. Okay, so here again, I'm going to assume that V and W are finite dimensional just for essentially this second step in the proof, but so I'll only state it for finite dimensional things. So suppose V and W are finite dimensional, and T is a linear map from V to W. Then the range of T dual is the same thing as the annihilator of the null space of T. Okay, further, the dimension of the range of T dual actually matches the dimension of the range of T. Okay, sorry, my thing keeps flipping. Okay, so let's actually prove the second statement first, because then we'll be able to use it in a nice way to prove the first statement. So let's prove that the dimension of the range of the dual map is equal to the dimension of the range of the original map first. Okay, well, we have the dimension of the range of the dual map. All right, so let me just point out that T goes from V to W, T dual goes from W to V dual. But by the rank nullity theorem, so this is by the rank nullity theorem, this is the same thing as W dual, the dimension of W dual, the dimension of the domain, minus the dimension of the null space of the dual map. Okay, but we already know that the dimension of the dual of W is the same thing as the dimension of W. So I can make that substitution there. And we just saw that this null space of the dual map is the same thing as the annihilator of the range of T. Okay, but then we also proved earlier that if you add up the dimension of a subspace and its annihilator, you get the dimension of the big space. So this, I mean, I can even give you numbers, at least from the notes. So this is by 119 and 107. This one is by what's going to be numbered 118 in the notes. This is the dimension of the range of T. Okay, so that proves the second statement. Let's prove the first statement. So now I need to show the equality of these two subspaces. Let's show that the first one is a subset of the other. Okay, then we'll show the opposite inclusion and then we'll be done. Okay, so let's suppose that phi is in the range of T dual. Okay, and remember the range of T dual lives inside of V dual, so this is a linear functional on V. Okay, well, what does it mean to be in the range? This means that there exists a psi in W dual such that phi equals T dual of psi. Right, if it's in the range of T dual, it means that it maps over from something to T dual by under T dual. Okay, I'm trying to show that phi is in the annihilator of the null space of T. So I want to show that if you take anything in the null space of T and you plug it into phi, you get 0. Right, so let's let V be in the null space of T. Then I'm trying to show that phi of V equals 0. Well, phi is just T dual of psi, That's all that map is. But T dual of psi is defined to be psi of T of V. Okay, but this is psi of TV. But remember that V is in the null space of T, so this is psi of 0, and since psi is a linear map, you get 0. This shows that phi is in the annihilator of the null space. Okay, so this shows this first inclusion, and I need to show that the annihilator of the null space is contained in the range of T dual. Or do I? So I said that we were going to use the second part to prove the first. Because now what we have is we have one subset contained in another. If I can show that they have the same dimension, then they must be the same. Right? This is another technique for showing that two subspaces are equal, so that one is contained in the other, and show that they have the same dimension. So just to remind, okay, so what have I shown? I've shown that the range of T dual is contained in the null space, the annihilator of the null space, and I know that the dimension of the range of T dual is the dimension of the range of T. But what's the dimension of the range of T? Well, by the rank nullity theorem, this is V minus the dimension of the null space of T. But now again, we have this result that if you add up the dimension of the subspace and its annihilator, you get the dimension of the space that it lives in. So this is the dimension of the annihilator. So I have this subspace is contained in this one, and they have the same dimension. So these two facts together give you that the range of T dual is equal to the null space, the annihilator of the null space of T. Okay, I mean, if you want, you can also prove the opposite inclusion directly. I mean, it's not a bad idea. It's maybe a good exercise that you should try. Okay. So we understand now this theorem tells us what the range of the dual map is. The last piece then should be, well, what about the surjectivity of the dual map? And there's, again, a nice proposition. Let's just start a new page. The following. So again, I'm going to suppose that V and W are finite dimensional. And T is a linear map from V to W. Then the dual map is surjective if and only if the original map is injective. Again, maybe a theorem you actually could have guessed, but we need to prove it. Okay, here's the proof. Okay, so certainly T is injective if and only if the null space of T is trivial. This we proved long ago and have used it many times since. Here's the claim. Claim is that the null space of T is trivial if and only if the annihilator of the null space is actually equal to all of V dual, I should say. Okay, notice that this proof is like somehow exactly like this proof except the opposite, right? So for this first proof that we did today, we started with T being surjective. That's if and only if the range was everything. And then we proved that the range being everything is equivalent to the annihilator being nothing. So this proof is like kind of the one that we're currently doing, It's like the opposite fact. And so we're using kind of the opposite proof, right? So we said that T is injective if the null space is nothing. And we're going to show that the null space is nothing if the annihilator is everything. Okay, so we just need to prove, okay, and then I should point out that we just showed that the annihilator of the null space is the same thing as the range of the dual. So by the previous result, this is the same thing as the range of T dual equals V dual, which is the same thing as T dual being surjective. So if I can prove the claim, then I'm done. Okay, well, let's prove it. Okay, so if the null space of T is just the zero vector, then every linear functional on V vanishes on the null space of T, because every linear map sends 0 to 0. Then every phi in V dual is, or then for every phi in V dual, phi is in the annihilator of the null space, right? Because every single map maps the null space entirely to 0 because the null space is just the 0 vector. So this shows that the annihilator of the null space is everything, assuming that the null space is trivial. Okay, well, what about the opposite direction? The opposite direction is the one that is we need to do something. So conversely, suppose that the annihilator of the null space is everything. Okay, well, this means that for all phi in V dual and for all V in the null space of T, phi of V equals 0, right? This says that every single linear functional vanishes on every vector in the null space. I'm trying to show that if the annihilator of the null space is everything, then the null space is trivial. So let's suppose for contradiction the null space of T is not just trivial. Right? Then there exists a non-zero vector V in the null space of T. Okay, now I'm going to extend. I mean, okay, I guess I could start with a basis of the null space, but it doesn't really matter for this. So extend to a basis of V. So I'm starting with V, and then maybe I'll take U1, U2, up through UN of V. Now what we're going to do is we're going to define a linear functional that maps V to 1, vanishes on the rest of the basis, and then that will give us a linear functional that doesn't vanish on the null space of T. But we can do this because we can send a basis anywhere. Okay. So define a functional phi such that phi of V equals 0 and phi of uj equals 1 for all j. But then phi is a linear functional in V, but phi is not in the annihilator of the null space because it doesn't vanish on the null space. But I guess I'm actually proving this by the contrapositive. I guess I'll make that clear in the notes. It doesn't really matter. The logic still works. But anyway, in this step, I'm supposing that the annihilator of the null space is everything. But here I found something that isn't in the annihilator of the null space, which is a contradiction. right? This means that the thing that we supposed must be wrong. That means the null space must just be trivial, which shows that this implication is correct both directions, which, as we discussed before, proves that T is injective if and only if T dual is surjective. Okay. The last thing that we're going to try to understand about a dual map is we're going to try to understand the matrix of a dual map, right? Because one very nice computational tool you have if you have a linear map is if you have a linear map from V to W, then you can take a basis of V and a basis of W and write down its matrix. Right, so recall a nice computational tool is if you have a map T from V to W, and you have a basis V1 up through Vn of V, and a basis W1 up through Wm of W, is you can express a matrix that represents T with respect to these bases, and it'll be an M by N matrix. Can study M of T, the M by N matrix of T with respect to these bases. Right, very nice computational tool. Now, what about T dual? From W dual to V dual. Well, we know that you can take, if I have a basis of V, I know I can take the dual basis. Let's call it phi 1 up through phi n. And similarly, I can take the dual basis to my chosen basis of W. Call it psi 1 up through psi m. Okay, then we get now M of T dual. And this is going to be an N by M matrix. And the question is, how is this matrix related to this matrix? I mean, it has not quite the same size, right? This one is M by N. This one is N by M, right? So if this one looks like this, then this one looks like this, right? If this one is, the top one is wide, then the bottom one is tall. Well, there is one operation that you know about matrices that plays with the size of the matrix in this way, and that is the notion of the transpose. Okay, so if A is an M by N matrix, then it's let's say the transpose of A denoted A superscript lowercase t is the matrix, is the N by M matrix whose jkth entry is the kjth entry of A. In other words, the rows of A transpose are just the columns of A. The columns of A transpose are just the rows of A. And so we have this operation that takes an M by N matrix to an N by M matrix. And it turns out that maybe the nicest result you can hope for is true. I don't think it's obvious at all. But if you take the matrix of the dual of a map, it's the same thing as taking the matrix of a map and then taking its transpose. Okay, really, really nice result, basically. Here, of course, I'm assuming all the setup on this previous part. So I'm assuming that I took the dual bases for W dual and V dual, and the matrix M of T is written with respect to the one basis, and the matrix of the dual is written with respect to the dual basis. Okay, and basically this proof is just an exercise in notation. So this is just definitions in notation. Okay, but let's at least discuss it a little bit. It's not like a particularly fun proof, but I guess I should do it for you. Okay, so let's get some notation. Let's let A be the matrix of T, and let's let C be the matrix of the dual, written with respect to these bases. Okay. Well, the entries, let's call them C, L, K of C, are determined by what, let's say by T of the psi k's in terms of the phi l's. Right, because this index denotes the columns. So if you fix a column, let's say you want C1, 1, C2, 1, C3, 1, C4, 1, C5, 1. That's a first column. The first column is determined by T of psi 1 in terms of the phi's. That's what I mean here. Right, so for each 1 less than or equal to K less than or equal to M, that's the number of psi's we have. That's the dual basis of the W's. T dual applied to psi K is just the sum L equals 1 to N of C L K phi L. Okay, another, all this is saying is that the kth column of C tells you what T dual does to psi K written in terms of the phi L's. Okay, but this, don't forget, this is an element of V dual, right? Because T dual went from W dual to V dual. So we can evaluate this map on Vj in V. It's a map on V, I can plug in a Vj. Right, so what is T dual of psi K applied to Vj? Well, it's just this map applied to Vj. But now remember that the phi's are a dual basis, right? These are dual bases to each other, which means that phi j of Vj is 1, but all the rest of the phi's on Vj are 0. So only one term survives. This is exactly Cjk. Okay, but meanwhile, so that's thinking about it in terms of the C's, which is the matrix of T dual. But we also have that this thing, we can think of the definition of what T dual does to a map in W dual. It just composes with T. Right, well, this is psi K of T Vj. But what is T Vj? Well, T Vj should be captured by the jth column of A, right? The jth column of A tells you the coefficients in terms of the W's for TVJ. So this is the same thing as psi k of, now we sum along the jth column of A, WL. Again, all this is saying is that the matrix A, the jth column of the matrix A tells you what T does to Vj. But now again, we use the fact that these guys are dual bases. That means that only one term survives when you plug it into psi. It's the kth term. So what you get is you get AKJ. So what does this say? Altogether, this says that the j kth entry of C is the same thing as the k jth entry of A. And since this is true for every j and every k, so this holds Cjk equals AKJ for every j and k, this means that C equals A transpose. Or yeah, which is the result that we wanted. Okay, so nothing particularly fancy going on here. That said, working with like these sums and thinking about these matrices is not an easy thing. So make sure you understand this proof. But there's no fancy theorems being used, at least. But this is a very, very, very nice result. Right, so if you're given a particular map from V to W, like a concrete actual map, the way that people actually study actual linear maps is, let's say 9 times out of 10 is you write down the matrix of that linear map. If you want to say the dual map, you just have to take the transpose of that matrix. It's a very easy operation, and therefore you can totally understand the dual map. So this is a very nice result. Because the dual map seems kind of a bit mysterious. I mean, even the dual basis seems kind of a bit mysterious, but it's all set up in such a way that the matrix of the dual map is just the transpose of the original matrix, which is really nice. Okay. Now, the last thing in this section is just like a little bit on the rank of a matrix. Okay. So we're gonna, I guess, I mean, it's in the section because some part of it uses duality a little bit. So I guess it's a nice concrete application of duality. I mean, it's not like the most profound one, but it shows that you can use some of the things that we've been developing. But let me, again, give you a flashback to 308. Which is given a matrix A, you can define the row space of A, the column space of A, and the null space of A. Okay, and if you use A to define a linear transformation, so this A, this gives you a linear transformation T from some vector space to some other vector space, then the column space of A is related to the range of T, and the null space of A is related to the null space of T, or the kernel of T. Okay, so I remember teaching this many times in 308. I've taught 308 kind of a lot of times. So you define the row space, the column space, and the null space, and then I sort of say, well, we're not actually going to talk about the row space all that much. The column space is important because it's the same thing as the range of the linear map. The null space is important because it's the same thing as the kernel of the linear map. and then the row space is something else. So one question that maybe should be lingering from Math 308 is, well, how is the row space related to everything? Okay, so what about me? Well, the row space of A, that's the same thing as the column space of A transpose. Right, because the rows of A are the same thing as the columns of A transpose. And we just saw that this is the matrix of the dual map. Which means that the row space should be related to the range of the dual map. Which is why it's not a thing that you talk about in 308, right? Because all this duality stuff is like, I would say, a level higher than the kind of stuff that you want to deal with in 308. So let's explore this idea a little bit. But let me just make the definitions that I need. So suppose that A is an n by n matrix. And so an n by n matrix. Then the row rank of A is the dimension of the span of the rows in F1n. Okay, so this is just a technical point, but right, a row in a matrix looks like, I don't know, something like this. And so it's not actually in F to the n because we generally think of F to the n as column vectors if we're thinking of them as vectors in this way. So it's like, it's a 1 by n matrix. It's a row vector. So this is just some very precise way of saying the span of the rows of A. They don't technically live in Fn, they live in F1n. Okay, the column rank of A is the dimension of the span of the columns. And let's put these on equal footing. Those are in Fm1. Right? You can think of them as m by 1 matrices, which is the same thing as a column vector. Okay, and I guess I won't prove this because I sort of already stated it, although you can read the proof in your book. If V and W are finite dimensional vector spaces, and T is a linear map from V to W, then the dimension of the range of T is equal to the column rank of the matrix of T. Okay, this is just this theorem, which I stated as one from Math 308. Of course, in Math 308, you probably use some kind of proof involving matrices and pivots or whatever. The proof in your book is an abstract proof. Okay. But now I'm going to use some of the stuff that we proved about duality to prove the following theorem. Proposition, suppose that A is an m by n matrix, then the row rank of A equals the column rank of A. Okay, it's not that obvious that this should be true. You take the span of the rows, it's some subspace. You take the span of the columns, it's some subspace. They're living in different vector spaces, right? One is kind of living in Fm, one is kind of living in Fn. They have a different number of vectors in general, but it turns out that their ranks are the same. And again, I guess you could do this by carefully proving some facts about Gaussian elimination and what it does to the rows and what it does to the columns. and then you can prove, say, that the row space is spanned by the pivot rows and the column space is spanned by the pivot columns or something like this. But we have all this duality technology. It turns out that we can prove this just abstractly, which is actually better. Okay, but because we proved a bunch of stuff. So given a matrix A, we can define a map T from Fn to Fm by what T does to a vector X is it multiplies it by A. Okay, then M of T is just A. Okay, and by the result I just stated, we know that the column rank of A is equal to the dimension of the range of T. Okay, but now note that the row rank of A, that's actually clearly equal to the column rank of A transpose, because the columns of A transpose are just the rows of A. So you're taking the span of the exact same vectors. So the column rank, sorry, the row rank of A equals the column rank of A transpose, which is the column rank of M of T transpose, which is the column rank of T, the matrix of T dual. Okay, but right, so here's where I'm using this fancy duality fact. But now the column rank of a matrix is the same thing as the dimension of the range. Okay, but now we prove that the range of the dual has the same dimension as the range of as the original map. And so we proved this today. But now by this fact, this is equal to the column rank of A. Okay, so this is maybe a fancy way to prove this fact, but it does give you, I mean, all the equalities on this page are sort of very easy. Whereas I think if you want to develop the proof by Gaussian elimination, we'd have to spend, I don't know, 30 minutes. So this is faster than that. Okay, but now the row rank of any matrix is always equal to its column rank. I should have circled this one, I guess. Which then, I guess, begs the question as to why we defined these two things. Why would we define two words when we actually only need one word because they're always the same? So in fact, generally you never hear column rank or row rank. The rank of a matrix is just its column rank or its row rank. They're the same thing. So someone talks about the rank of a matrix, they mean the dimension of the column space, which is the same thing as the dimension of the range of the linear transformation, which is the same thing as the dimension of the range of the dual map, which is the same thing as the dimension of the rows of the original matrix. Okay, so I guess this is kind of short today because this is the end of chapter 3. So, why start chapter 4 when you have a midterm on Wednesday? So Friday well actually, okay, so here's the plan. Okay, so Wednesday you have a midterm which covers everything up through lecture last Friday. So nothing from today, although I don't think we did all that much new stuff today. We didn't really introduce too many new definitions or anything today. We sort of just used all the definitions we had before. So, I mean, it's not like if you think hard about this lecture, you're thinking hard about taking duals, taking annihilators, which could be on your midterm. Okay, then that ends chapter 3. So then we have chapter 4. But chapter 4 is on polynomials. It's actually not on linear algebra. Nevertheless, it contains some like very important results for polynomials that we will want to know. So I will cover the results that I want to cover in that chapter, but we'll do it quickly. It won't take the full lecture on Friday. The good thing is that all the proofs and all the details are in there. So if you feel a little rusty on polynomials, then you have that as a resource. And then we're actually going to start on a little part of 5b called polynomials applied to operators, because it's sort of independent of the rest of 5b. Okay, so actually next time, we'll do sort of some pickings from chapter 4, and then a bit of 5b. And then next week, we'll go back to 5a and work through 5a, 5b, 5c in excruciating detail. And then, yeah, then I haven't thought about what we're going to do after that. But the plan is, I guess I should say Wednesday midterm. So no lecture that day, just do and upload your midterm. And then Friday, we'll hit some of the polynomial stuff, and then we'll talk about polynomials applied to operators. Okay.